Now that we have the surface that we're going to be using as the source, let's just clean it up. It's always a good idea when you blast out some points. It's a good idea to just apply a clean. It's easy to do, and it can help you get rid of some inconsistencies that you might have on your geometry or some isolated points. After that, I'm going to use a scatter. And we're not going to be using this geometry. This geometry, even though it's pretty balanced, but it might not have the density that we need later on. So it makes sense for us to just scatter some points. I like to use the density scale instead of using the force total count. It's easy for me to kind of scale it up. And if the surface changes, it's going to be dependent on the area and not on anything else. So let's multiply this by 10,000. How many points is this giving us? So 3,000 points. That's fine. It's a good number. It shouldn't be too slow. If you think it's slow, or if your system is kind of taking a while to calculate something, just half of this is going to be fine. So instead of 10, maybe 5,000. Yeah, 5,000 is good. It's going to be faster this way. So we have our points, but as you can see, these are not animated, but they need to be. So we're going to use a pointy form for that, for transferring the animation. And this is what we want to deform. We're going to also use the time freeze as the second input, which is the rest point lattice. And I'm going to just click this, hit Alt, and click again to set an elbow here. And then we'll use the actual animated mesh to deform. So now we should see the points rotate. Okay, attached to that surface. Fine, awesome. So the next step is going to be for us to set up some parameters for this. And as we saw before, we need to take care of a few attributes that are pretty important for this. One is going to be in the density, of course. The density is going to control how much smoke is going to be generated. So that's one. The temperature is also going to be important in this case. And from what we discussed earlier, where we said that the friction on the area where the rubber is hitting or connecting to the ground, the friction there is going to heat the rubber, and it's that rise in temperature that's going to generate the smoke. So the density and the temperature are actually going to be connected. For now, we're going to be thinking of temperature mostly. The other thing that's also very important, as we saw in the previous lessons, is the velocity. Okay, we really need to have some interesting velocity going on and being transmitted to the generated smoke in order to have an interesting simulation. So that's also something that we're gonna want to keep in mind, and we'll start with the velocity. So once you have the points moving, we can use a point velocity to calculate the velocity. Okay, this will give us some velocity, and let's have a look at those trails. So we have the option to visualize the velocity trails. So everything looks good in the beginning, but as the tire starts to speed up a bit, we notice that the trails kind of go into weird directions. Okay, these trails. The problem with these trails, what's happening is that when Houdini is analyzing the position of one point at a particular frame and the point on the previous frame, it's going to generate a vector between those two positions, and that's going to be the speed vector. But since we're moving in circles, Houdini doesn't have a way of knowing unless we kind of increase the frame sampling quite a bit. But that can also be kind of weird. What's going to happen is that it's going to generate this type of inconsistency. We know the direction of each point is going to be around the circle, but as it gets faster and faster, we lose a lot of accuracy on this calculation, and the direction is going to go wrong. It's not going to be the correct direction. So we need to fix this manually. One thing we can actually take out of this is we can actually use, even though that the displacement isn't correct, it can give us at least an idea of the scale of the increasement of speed that we see here. So I'm going to turn on the calculate speed, and I'm just going to use the speed. Out of this point velocity node, the main thing that I'm going to be taking out of this is going to be the speed. But the vector that I want each point, the velocity vector that I want each point to follow, is not going to be coming from this. We're actually going to be getting it from a spline. And like I was saying, this it is supposed to be a circle. The wheel is just spinning round and round, so the vectors need to follow that direction at all times. It doesn't make sense to have these crazy vectors. We need tangents to the circular motion. So the way I'm gonna do that is after the polyfill, I'm just gonna create a blast. And I'm gonna blast everything that's not the patch. And out of these, I'm gonna blast, I just need one of them. Let's say 0. So now I have this, and I want to convert this into a spline. So I'll create a carve. I have my spline. And finally, what I'm going to be doing is I'll create a resample. So the resample node will allow me to calculate those tangents, the direction. We have here a tangent attribute, and we can also, if we need to, or if we feel we need to resample the spline. I don't think we do. We have a lot of geometry already coming in, so I'll turn this off, and as you can see, we already have 128 points all around, so that's fine. If you want to have a look at the tangents that are being generated, just hold Control, middle mouse button, and then hit tangent, and it should show you the tangents. It's if you right click here on this little light bulb, you have the tangents and it's activated. So it's not visible because you need to set it up. Yep, just needed to update that. So as you can see, we have the proper vectors. Okay. This is because the spline is actually open, but that's fine. We have the directions that we want. This isn't going to be all that important. So what we can do is at every time we want to make sure that all our points are using these directions as velocity directions. What's going to change is the intensity or the speed, the size of the velocity vector, which is going to be based on the speed. Now we have an option to get those directions from. So now that we have that, I'm going to create a point per angle, and I'm going to call this set V. And I'll connect to the second input, that source of the velocity vectors that I want to use. So we need to get the nearest point for every point in here. I want to get the nearest point here and get the tangent u vector that that point has. Okay, so the first thing we want to do is get the nearest point from coming in from the second input. So it's an integer variable. It's going to be called refpt, and it's going to be equal to near point input 1 based on my position. The next thing we want is a vector variable where we're going to store the tangent u attribute from that point. So we'll say point from input 1. The attribute is tangent u, and the number of the point is going to be the refpt. Finally, we'll say that our velocity is going to be equal to that vector times our speed. Now, if you have a look at the trails now, we should see that we have the proper direction. Okay? Now, these vectors, these values of velocity are probably going to be too strong for us to be able to calculate the effect that we want to calculate with a reasonable number of subframe sampling. And that's always something that's going to make our simulations longer and more demanding in terms of hardware. So we'll establish a clamping value for the speed. I'll say that instead of multiplying directly by the speed, I'm going to multiply by a clamped speed. It's going to be clamped between 0 as a minimum value, and as a maximum value, let's use a channel for this. Let's say max speed. Let's create that channel, and let's say the max speed is going to be 5. Might be too small. Let's go with 8. And this is something that we can come back to later on to kind of based on the results that we're getting from our simulation. But this seems like a reasonable velocity vector. Now, this is much better than what we were getting from the point velocity by itself. Okay, this is much more correct. But we need to add some variation to this. Okay, so for that, I'm going to use a point VOP. I'm going to call it add vnoise. And I'm using a point VOP because I prefer to use VOPs for working with noises. Let's dive inside, and I'm going to use a 4D noise. And for that, I'm going to go with the curl noise. 4D just means that besides having considering 3 coordinates, it actually considers a 4th coordinate that we usually associate with time. So instead of using a 3D noise, let's go with the 4D noise. So we're not going to be sampling just position. As you can see, the color changed from green to yellow or lime. And what I'm going to do is search for a vector to vector 4. And we'll grab the position and the time. And this is what we're going to be sampling. Now, the idea of all this is going to be to add this curl noise vector to our current velocity vector. And that's what we're going to be outputting. Already you can see we have some noise going on, which is changing through time. Great, but let's work on the scale of this. So it seems that we have a frequency that's too low. We want smaller detail. So here on the curl noise, let's try something like 10, 10, 10, 10. So this means that it's going to be changing like crazy. And we have a lot more things going on. The amplitude is too wild, so let's go with 0.1. Seem reasonable. Okay. Now we also want to make sure that when we're going slower, we don't have as much noise. And we can also use the speed value, not only to control the intensity of the curl noise, but also to control the frequency at which the curl noise is actually changing. So let's get that speed attribute that we already have. So let's create a bind and make sure that we're loading in the speed. And we'll first normalize the speed based on the maximum value that we have. Let's see here. Let's go to one of these frames and check the values that we have for speed. So it's close to 14, so let's use that as a way of normalizing this. Let's divide the speed by a constant. And let's say that constant is 14. So now we have a value of speed that goes from 0 to 1, and we can use that to multiply whatever's coming out of this curl noise. And we should see that when we're at maximum speed, we have all 100% of the contribution of the curl noise. But when we get lower and slower and slower, we see that we no longer have those crazy vectors being applied to the velocity vectors. If we don't have this, then even when we're slow, we get some crazy vectors, which doesn't make much sense. So the other thing you could do is, this is going to be much less noticeable, but what we can do is play with the frequency. So now we have a frequency of 10, 10, 10, 10, but we can actually use the velocity values as a frequency as well. So let's create a float to vector 4. And I'm going to create a constant, so it's easier to control constant. Let's say 10, and we'll use 10 for all 3 axes, 1 and 3. But the 4th one is going to be controlled by the value of the velocity. So this means that when it's slower, we'll have a smaller frequency in terms of the fourth coordinate of the frequency. So the fourth coordinate affects how fast the kernel noise is going to be evolving. So so in this case, when it's faster, it's going to be evolving faster as well. We're going to have more turbulence on the movement of these vectors. So yeah, and with this, I think we have a nice velocity vector